So here's the name of the game today. We're going to have an abbreviated Math Material Monday today, because I want to make sure that the first half of the course sort of culminates in this application of the mathematics that we've been learning up to this point. And it's one of these applications that I feel like, as mathematicians, we should know kind of what is the wizard behind the curtain on this. And it is how to fit an equation to a set of data, how to find a curve or an equation of best fit for a set of data points that you've been given. This is something that I was just observing a tutor in math services this morning talking about with a student taking an elementary statistics course. They're learning linear regression. A student says, well, how are we supposed to do linear regression? They give us a set of 16 different points, and we have to find a line of best fit through those 16 different points. How are we supposed to do that? And the answer we always give in math services is, well, your professor has told you how to use some technology to make this happen. They've showed you how to use your calculator. They've taught you how to use Excel. And just plug all your data into Excel and ask it for the equation best fit, right? Which is great, because Excel is perfect at doing that kind of thing. It's one of the things technology was just designed to do. But as mathematicians, let's figure out what's going on behind that curtain, that technology. How does this all work? And more importantly, how can we harness it to find equations of best fit that are not necessarily straight lines? But if we have a particular kind of equation in our own minds that we'd like to fit to a set of data, how can we do that? And in particular, how can we do it when we can't expect that that curve will exactly go through all of our data points? So your 5 different groups today are going to be working on 5 different kinds of equation models to fit to a set of data. You'll all have the same set of 3 data points to work with in just a moment. And before we actually get into the weeds of sort of mathematically how does it work, what I have for you is a set of Mathematica applets, things that look like this. And what these applets will allow you to do is to take a equation model. So in other words, I'm going to be looking at how to fit an equation of the type something times the square root of x plus something times 2 to the x equals y. So y equals something times radical x plus something times 2 to the x. And it looks like in this example I'm calling this something, this first something m and the second something b, but that's not really important what we call them. Whatever we call them, those unknown parameters are what we're trying to find, right? We're trying to find values of those unknown parameters that will make our graph fit our data points as best as possible for whatever that means. So what this little applet is going to allow you to do is to just play around with those parameters. So right now, m is equal to 1, m is equal to 0, b is equal to 1. So if I play around with those by dragging these sliders, I'm going to get my graph to change. So here I'm playing with the coefficient of 2 to the x. If I don't have a whole lot of 2 to the x in my equation, then pretty much my curve looks like a square root function. But the more 2 to the x I put into it, the more it begins to look like that exponential curve. I can also flip the coefficient around to be negative so that I have this competing square root of x behavior and now a negative going 2 to the x behavior. So I can tweak this 2 to the x amount around. I can also tweak how much square root of x I have as part of my function. And as I do so, what you'll notice is that these little blue bars here, those bars are measuring how far away from the data is our graph, as the difference in y values between the y values of the points themselves and the y values of those points on the graph, which has the same x values as those y values. If I take those distances and I square them and I add them all up, then what I get is called a squared error measurement. And what we're interested in doing is finding that curve for which that squared error measurement is as small as possible. So this little applet is kind of keeping track in the upper right-hand corner of what the current amount of squared error is, as well as what's the smallest amount of squared error that we've found so far. So this amount that I have now is more than my minimum, so this is not my best fit. I'm going to actually reset this real quick. Just back to my initial settings. That didn't quite do what I wanted. And so by sliding these around, we should be able to find a minimal value. I got down to 1.3. That looks pretty good. I think we did a little bit better before. Maybe if I drag this up a little bit. About 1.19. Got a little better. So it's kind of an experimental science in the beginning. But your job as a team will be to select one of the models, and each of your team will have a different model to play with, and figure out how small you can get that minimal squared error to be. And then the equation that realizes that minimal amount of squared error is the equation that you'll get down here in the lower left.